Assalamualaikum. We are from section 2, group 1. Today we want to present the last week assignment from the subject Analog Electronics DEKE 1213. The title of the assignment is Wein Bridge Oscillator. Okay, this is the list name of our group. Okay, first is my name, Muhammad Adib Ikhwan. Second, Muhammad Adam Wafiq. Next, Muhammad Kasyful Azhim, and the last Muhammad Ilyasa. Okay, this is the first slide from we presentation. Okay, the first slide is about introduction. Okay, the Wein bridge oscillator is a type of electronic oscillator that generates sine wave. It is a two-stage RC circuit amplifier circuit with high horizontal frequency quality, low distortion, and tuning capability. Consider the extremely simple sine wave oscillator employed by the RC circuit and place it in the ordinary LC circuit. The output of the sinusoidal waveform is referred to as an Wein bridge oscillator. A Wheatstone bridge circuit is another name of the Wein bridge oscillator. Next, the Wein bridge oscillator is used to find unknown values of component. In most of the case, this oscillator is used to induce audios. The oscillators are designed simply, size is compressed, and it has stable in frequency output. Hence, the maximum output frequency of the Wein bridge oscillator is 1 MHz, and this frequency is from the phase shift oscillator. The total phase shift of the oscillator is from the 360 degree or 0 degree. Okay, next to the next slide. Thank you.
Okay, today I want to present about the circuit diagram. Okay, so this is the two-stage amplifier with an RC bridge circuit with a lag networks. Okay, so when the frequency increase, so the lag at the phase shift will increase, while when the frequency decrease, as the lead also decrease, so it's vice versa. Okay, furthermore, this Wein bridge oscillator has a specific frequency, so it become more sensitive. Okay, this bridge has a phase shift of 0 degree at this frequency. Okay, Wein bridge oscillator circuit diagram is shown in the diagram above. Okay, R1 is shown in the series with the C1, while R3 and R4 and R2 are shown in parallel with the C2 to form the 4 arms. That's all for me, thank you.
Operation of the circuit, startup condition and sustain condition. The Wein bridge oscillator employs a feedback circuit comprised of a series RC circuit connected to a parallel RC circuit of the same component values, resulting in a phase delay or phase advance circuit depending on the frequency. The phase shift is 0 at the resonant frequency. Consider the following circuit above. For startup condition, the amplifier's closed-loop gain must be greater than 3 until the output signal reaches the desired level. Ideally, the amplifier's gain should be reduced to 3 so that the total gain around the loop is 1 and the output signal remains at that desired level, thereby sustaining oscillation. For sustained condition, the voltage divider circuit has been changed to include an additional resistor in parallel with a back-to-back Zener diode configuration. When the power is applied for the first time, R3 Zener diode appears as open. This connects R3 to R1 series and will lead to increasing the amplifier's closed-loop gain as shown below. R1 equal to 2R2, so as the ACL equal to R1 plus R2 plus R3 R2 equal to 3 R2 plus R3 R2 equal to 3 plus R3 R2.
Hello and Assalamualaikum. I'm Muhammad Kasyful Azhim. I want to take over to tell about the important formula with derivation and calculation related on Wein bridge oscillator. So this is the expression for frequency of oscillation of Wein bridge oscillator is given by Fr equal to 1 over 2 pi Rc. So I want to explain the long derivation for how we can get the frequency of Wein bridge equation. So we move to the first step. We have the feedback factor of the gain of the feedback network beta is defined as beta equal to Vf over Vi, and directly get the first equation. Then second step, the Vf is the voltage across the parallel combination of R2 and C2. Let the impedance of the arm which has R1 and C1 in series be Z series, and the arm which has R2 and C2 is in the parallel be Z parallel. Therefore, we obtain the two equations which are the Vf equal to Zp over Zp plus Zs times Vin for the equation 2, and we get the beta equal to Zp over Zp plus Zs, and we get the equation 3. Okay, now we continue with the step 3. So from the step 3, we obtain the two equations for Zp and Zs. So for the Zs equation, we consider as the equation 4, and the Zp equation we consider as the equation 5. And then we move to the step 4. We substitute the equation 4 and 5 into the equation 3, and we get the new equation like this. And then we move to the step 5. We substitute the above equation and solving for the beta value, and we get the new equation for equation 6. And then we move to the step 6. We substitute the equation that related into equation 6. So we get the new equation, which is the equation 7. And then we move to the step 7. We rationalize the equation 7 to get the long equation like this, and directly get the equation 8. Okay, for the step 8, as the mentioned earlier, the phase shift introduced by Wein bridge circuit at the desired output frequency should be 0. For that, the imaginary part of the equation 8 should have a 0 value. So the derivation from the equation 8, we already obtained the frequency equation, which is we consider as the equation 9. And from the expression for the oscillator frequency, we summarize at the last step, which is step 9. If we substitute and consider the value R1 equal to R2 equal to R, and C1 equal to C2 equal to C in the expression for the oscillator frequency, then the equation 9 gets modified as follow equation, which is equation 10, and the latest oscillator frequency equation, which is 1 over 2 pi RC. So there are another calculation to find, such as capacitive reactance and impedance from the circuit. So to find for the series circuit, to find the capacitive reactance, we can find with formula 1 over 2 pi FC. And to get the total impedance for the series circuit, we can use this formula. Okay, for the parallel circuit, we know that the capacitive reactance Xc is the same value with the resistance value, which is the R2. So we can find the total impedance of the lower parallel Z with the formula 1 over Z equal to 1 over R plus 1 over Xc, and we can get the total impedance. So we move to the second point. When Xc equal to R parallel with Xc and R equal to Z, we can find the vector sum of this parallel impedance with this formula. And finally, we can get the total output impedance, which is the combination of series and parallel. We can get the total output impedance with this formula, which is the Z output equal to Z parallel over Z parallel plus Z series. Okay, this is the application of Wein bridge oscillator. So the first application of Wein bridge oscillator is used in distortion testing of power amplifier. The second one, it is used to measure the audio frequency. And the third one, Wein bridge oscillator can even be designed using operational power amplifier as a part of their amplifier section. So how Wein bridge oscillator apply it? It is to be noted that here the operational power amplifier is required to act as a non-inverting amplifier as the Wein bridge network offers zero phase shift. Further, from the circuit, it is evident that the output voltage is fed back to both inverting and non-inverting input terminal.
Okay, before we end the presentation, this is a three reference we use to make a research about Wein bridge oscillator. Okay, I hope you enjoy the presentation and thank you.